Oh, yeah. It's official. Thank you. I bought this outfit for my job interviews and pulling it out again. Thanks, thanks. I thought about it. I thought about pulling out Sam and the vision stick, but yeah. So I made a new image at the end of my 4 blenders and a chemical bomb. So like, you don't want these things flying in here. My hot take is safe control requires robust implementation. And I built these, so. No. It broke after. I actually think that one broke when I was moving it, not when it was flying. Ames, Joel, Yisong, Gunter, Preston. Yeah. He almost came. Yeah, but he said he'd just been doing a bunch of traveling and it didn't quite work out. It's a long flow. Oh, this is so much better than my job talk because I know all these people and they're here to support me. It's nice. Yeah.
Video.
Howdy.
This is it.
Yeah. Member of the committee. Yisong. Yeah. I like this is recorded. I like all of them. Thanks. How's it going? Thanks for coming. Hi, Joel. Thank you. Sorry. If you do, that's fine. Hopefully I'm not too boring. We've got the whole committee. I think we're set.
Who's the chair?
Joel is the chair.
Joel.
Back to back. Do you want a microphone?
No. When do you want to get started? People, so I will turn it over to Aaron to say a kind words about a couple things here.
Got the mic?
To a big audience, yes. This is an impressive audience again. I think it speaks to Ryan's involvement in the community. It's been he's been actually an integral part of the lab for his whole time, helping people, always a helping hand. I think what's been interesting about his work is first bringing perception to the loop, which we're going to see, which is something I was always very scared of, but he pushed that envelope. And secondly, stochastic stuff, which I'm also something that I'm very scared of, and he pushed that envelope. I think the highest compliment you can give to a student is when they teach you a lot of things you didn't know, and I've learned a lot from Ryan over the years. So I think with that, we should hear what he's learned through this process as well. So excited to hear you talk, Ryan.
Thanks so much. Well, thank you, Dr. Ames, for those kind words, and thanks everybody for being here. I really appreciate it. So today I'm just going to go over my work on dynamic safety under uncertainty. And to do that, I'm going to this is the overview of the presentation. So I'm going to start with some motivation, go through my work, and end with some takeaways and future work and conclusions. So I want to just start this out by thinking about the science fiction robotics that we can imagine for the future. There's really exciting things that we can imagine, like the autonomous vehicles here from Minority Report, or the Iron Man suit, or my personal favorite robot, Baymax, down in the corner. Like, we've got some really exciting robots we can imagine for the future, but we're not quite there yet. We're kind of over here on the left-hand side, where our robots are good, but we're not achieving the future we want. And I want to ask, what is preventing us from achieving that future? And I would argue that a huge hurdle that we have yet to overcome is this idea of dynamic safety. We need our systems to be strong enough to achieve their goals while also being smart enough to avoid accidents while doing it. And this is what I consider kind of to be the current status of safety for robotic systems. On one hand, we have robots like the Roomba. So this is what I consider to be safe by mechanical design. These are phenomenal systems. Like, a lot of people have Roombas. They're really impressive in getting robots into people's hands. But they do that in part by just being able to be super safe by design. They can bump into you, they can flip over, it's not going to be a big deal, they're not going to cause any serious problems. But in doing that, they sacrifice performance. So they're not able to lift the carpet and vacuum underneath it. Me and a vacuum cleaner is significantly better than my Roomba, but because it's safe, we're able to deploy it. The second category here is safe by regulation. So this is the Animal Quadruped. This is a group out of ETH. Marco Hooter's group designed this robot, and they're deploying it in industrial settings. So it's going places where people can't go, robust or complicated terrain, like in caves on oil rigs, stuff like that. But when they brought it out, they were doing this demo, and I took this picture with my cell phone, and they have this sticker on the side that says, keep 2 meters distance. And so essentially what they're doing is, instead of making the robot safe, they're just saying, by regulation, it has to be away from people, and so it's inherently safe that way. And so these are like our very performant robots, like our industrial robots. You know, we don't see the robots building cars. They're behind fences in industrial manufacturing plants. So these are our two kind of ways of industry has found to deploy robots at scale in a way that's safe. But this isn't necessarily what we want long term. I would say that these are kind of our training wheel approaches to achieve safety. It works, we get people on a bicycle, but they're not the full bicycle that we ultimately want. The third category is the one we really don't want to be in, and these are systems that are insufficiently safe. And the bar for safety obviously varies per system, and just as an example, I'm going to focus on this autonomous vehicle scenario of Cruise. So Cruise was an autonomous vehicle company. They were deploying their robots, giving taxi rides in San Francisco, and they accidentally trapped a pedestrian under the car and dragged them across the street in a collision event. And so they were trying to be safe, pulled to the side of the road, but they had trapped someone underneath the car and caused serious injury when this happened. Ultimately, GM decided to shutter the company. And so we really can't afford to have these things happen as we're deploying robots at scale. I mean, we hold robots to really high bars for safety. People get in car accidents all the time, but when an autonomous vehicle does it, because we hold robots to such a high bar, it can really affect the industry and our general deployment. So we need to be really careful as we develop the performance of these systems to develop safety alongside it. And robot performance is going like crazy right now. Over the course of my PhD, we've developed some really insane capabilities in robotics. So on the top left, this is Boston Dynamics and the AI Institute. This is their new Atlas robot doing some pretty crazy dance moves. Bottom left, this is Unitree's quadruped, doing some amazing locomotion with these wheel legs. And then my favorite video of the three, this is on the right. This is Blake and Gary, who I believe are somewhere in the audience, members of the lab, who got this Unitree G1 humanoid on Friday and had it up and running like this on Sunday. So we're really developing amazing capabilities for robotics. I mean, this speaks to them as engineers, but it also speaks to our ability to get these systems up and running and deploying them. And so we're developing this performance really quickly, and we're kind of moving towards this schema for how we're deploying these systems. We've got really complicated controllers, reinforcement learning LLMs, VLAs, VLMs, foundation models. We're really going crazy with all these things we can do, and then we're deploying it on systems in safety critical scenarios. Some folks in the industry want robots to be babysitters. And this, to me, is really concerning. Right? We're holding robots to a really high standard of safety, but then we're trying to deploy these kind of black box algorithms onto robots in really safety critical scenarios. And so what I'm going to advocate for in the space that I like to work in is this idea of a dynamic safety filter. How can we come in between these complex controllers and the true system and make sure we get practical safety guarantees, practical deployable dynamic safety on our real world systems? And just to give you an understanding of where I try to live with this, so on the left, we've got safety liability, and on the bottom, we've got performance. And the dynamic safety filter should be able to move you across different levels of performance based on how confident you are in your system, while always staying safe. So if you have low confidence in your system, you can use worst case conservative guarantees to maintain safety at the cost of performance. And as you build confidence, you can move towards a more nuanced risk-based understanding of safety. And we can move in between these by leveraging data-driven methods. And these are the three components of my work for the thesis, are these deterministic guarantees, leveraging data to improve, and then winding up at risk-aware safety. And so we're going to start off with just trying to rigorously define safety. In order to guarantee it, we first have to have a mathematical description of it. And so when we, as humans, look at these scenarios, it's pretty clear to us that they're unsafe, right? But how do we encode that mathematically? What do we mean by safety? So we're going to start with this example of an autonomous vehicle. And we're going to say that it has some state x. And x represents things like the position, velocity, orientation, angle rate, things like that. And then it has associated dynamics. So these are like our Euler-Lagrangian mechanics, or just F equals ma. This allows us to understand how the system will develop through time. And then there's a region of space that we are OK with our system being inside of. So this is within the lane lines. It's not colliding with the other vehicles. We're OK if our system is inside of this green set C. And we're going to define safety as staying inside of that set C. So we're defining safety as the forward invariance of our system within this safe set. If we define the safe set as the zero superlevel set of some function h, so that looks like this. So this C that we had before, we turn it on its side, and now we're describing it using this function h that describes the value of safety. Then we do this really nice associated theorem that says if we lower bound its time derivative by negative alpha h, then we get safety. And visually, it looks like this. So the blue dot is our system. It's moving towards the boundary of the set. The value of safety is decaying on the top, but then we're forcing the time derivative of safety to go upwards, and this means that the value of safety can never dip below 0. There's also a cool result that says this goes the other way. So this is a good characterization of safety because under some minor assumptions, you can start with safety and then get this H description of safety for our system. This is growing in popularity. There's like, when I looked a couple of days ago, since they came out as an idea, there's been like nearly 5,000 publications, lots of conference sessions, workshops, and things like that. And people generally apply the safety ideas in this form of a safety filter. So we're going to take in the safety definition, a user command, a system model, and a system state, and then put it into the safety filter that's going to minimally modify the user command in order to enforce our safety constraint, this decay constraint here, producing a safe input. And this looks a little complicated, but really, this is just an if statement. So if your nominal controller is safe, use it. If it's not safe, then we have this modification term that we can add that's all analytical functions, so we can do this in real time. And a lot of folks have been working on this. So we've got a group at Georgia Tech, now UCI, Magnus Egerstad's group, who put these on these mobile robots. Marco Hooter's group at ETH with the animal quadruped, making sure we get safe foot placement for this quadruped here. Bottom left is Choo Choo Fan's group at MIT, making sure that our quadrotor drones aren't colliding with each other or the obstacles in the environment. And then on the bottom right, Gabor Aratz's group at Michigan, making sure that these cars don't collide with each other. So a lot of people have been applying these. My first year of my first year of graduate school, I was really excited. I had taken all these classes, I'd learned the theory, I'd seen these things deployed, so I was excited to go put them on robots. And these are my first applications of these things to robots. And we're not getting the safety that we want. So our drone falls to the ground, our systems hit their obstacles, and we're not achieving the safety that we thought we had from theory. And okay, what happened? How do we get safety in the real world? And I would argue when I tried to apply these naively, I didn't satisfy the assumptions that I made in my theory. And in particular, I violated these three assumptions. One being, I assumed that I had a perfect understanding of my system model. I assumed, two, that I had a perfect measurement of my system. And three, I assumed that I had a well-defined understanding of safety. So my safety definition was consistent with my system dynamics. In general, none of these things hold for real-world systems, so we need to look at ways to robustify against these sources of uncertainty. So to start, we're going to look at the perfect model case. So in general, I don't have the perfect model for my system. And we're going to say that just for simplicity here, we have an additive disturbance, D, that comes in as a matched uncertainty to our input, and this is bounded by some value delta. And when we enforce safety nominally in this case, we get an expansion of our safe set. So we don't keep our original set safe, but now we have a slightly larger set, and that expansion is based on this value delta. But there are ways to counter this. And so if we add this tightening term, we can make sure that this expansion doesn't get too big. We can counteract it. And so on the bottom right, you see this set can expand, or as we make eta go down towards 0, we can recover almost the original set. So we can counteract the effect of these dynamics uncertainties. Okay, so that's a way to get around the first violated assumption. We can tighten this constraint a little bit to avoid having that error affect safety too much and to ameliorate it. Second, what if we don't know exactly where we are? So if we don't have the perfect understanding of our state, but we have some misunderstanding in where we think we are, this is what can happen. So I'm trying to use vision on board to make sure that the segue doesn't hit the blocks, but the vision system is deviating from the true state. So on the top right, you see the true state is a solid line. The measured state is the dotted line, and they're deviating. And so we think we're keeping the measured state safe, but we're not actually doing that. So we end up with a safety violation. Our system hits the blocks. And so we can get around that by doing the same thing we did before, where our true state and our measured state, we're going to assume has some bounded difference between them. So now there's this epsilon term, and we're going to take a similar approach, where we're going to tighten our safety constraint. This involves a bunch of Lifshitz constants. It turns into a second-order cone program here. But we're going to tighten this constraint, and what that allows us to do is pick a single input that ensures safety for every possible true state within this uncertainty ball. So if our measured state x hat is this one here, and our true state is within some radius epsilon, then this constraint allows us to pick a single input that keeps the whole uncertainty ball safe. And we deploy that on hardware. And since our solid line doesn't exit this blue region around the dotted line, we have a valid safety guarantee to make sure we don't hit the blocks. And this is essentially just shrinking our safe set, but it's doing it in every dimension. So our position, velocity, pitch rate, and things like that. Okay, so that's a way we can get around measurement uncertainty. And then finally, I want to talk about this well-defined safety idea. And this one's a little more complicated. Um, it has to do with the fact that starting with the joints of the system to define safety can be kind of complicated. This ends up being like a reachability problem. It can be really hard to solve. And essentially, it's that if I don't want to hit the door, how do I need to actuate my legs in order to not hit it? Like that can be kind of complicated to describe. But if I don't want to hit the door and I can just actuate my velocity, that's a lot easier to describe. I just need to slow down as I get close to it. And so using that kind of idea, we're going to start with describing safety in terms of outputs. So instead of starting at the joints and the bottom up, we're going to kind of go from the top down and start with the system position and then key components like the shape and its ability to track these outputs. So in that way, we can just describe each of these systems as their outputs and their associated shape. This borrows a lot from this hierarchical understanding of controllers for robotic systems, which is a really common paradigm. If you were at Dr. Knoll's talk yesterday, you got a good understanding of this, but I'm taking the same approach here where we have 2 layers and then a real world system. The reduced order planner up top is going to provide some sort of reference command, or it could just be me with joysticks. And then the tracking controller is going to try to follow that reference. And it's going to do that by actuating on the real world system, applying torques or voltages or whatnot. The real world system then moves in its state. The tracking controller uses that state to try to track it and provides some guarantee of tracking up to the reduced order planar, codified here as this Lyapunov convergence. And the systems we're going to work with have this kind of structure. So I've got my real world system on the bottom, an associated tracking controller that allows us to simplify our system down to its outputs and its associated shape. And so we came up with this cool theorem that says, as long as the true system tracks the simple system fast enough, then we can use the simple system to make safety guarantees. And so precisely what I mean by fast enough is if I'm enforcing this constraint with my simplified system on the output, so like a single integrator system, then if alpha is really big, we must be able to track our system really fast. If alpha is really small, then we're allowed to be slower in our tracking of the simplified system. And on the right here, you can see what this looks like. So we describe safety for these 2 systems in the exact same way in terms of its safety requirements. So we're saying, don't enter these circle regions around the columns. And this is allowing us to achieve safety for both the quadruped and the quadrotor drone. And the key idea behind this is that we start with a safety requirement that's easy for us to describe. And this might be our center of mass position needs to stay away from the obstacles in our environment. And then we're going to subtract off a tracking metric. And this is going to describe safety for the full system. And this is a really rich idea. We've published a bunch of papers that really play with this theme, either starting with an unknown tracking controller or building it up through methods like backstepping or things like that. So just one more time to look at this. I describe the safety of this robot based on its output, so its position, and then choose safe velocities, which are then tracked by a locomotion controller to move it across the room and avoid entering these unsafe regions. Same thing happens with our drone. This one's a little harder to see just because of camera perspective, but the plot on the right shows you how safety changes in the environment. And we're describing safety for these 2 systems in the exact same way. They're just using different tracking controllers underneath. And then here, this one's pretty cool. So it can't move sideways very well. And so it has to turn in order to track the safe velocity, which is aligned with the treadmill. And so as the treadmill starts to move it outside, Sorry about that. Does this work? Okay, I'll hold it a little farther away. Okay, so here we've got our robot. We've generalized we tune the parameters to the outside scenario a little bit more and move the blocks around, wanted to see how these parameters generalized, and it's working really well. So we're able to navigate these scenarios we didn't originally train on, nicely navigating across this field now with different visual information, different locomotion environment, things like that. Okay, so that was a way we could identify how much robustness we wanted. But why can't we just reduce how much robustness we need? So in this case, we might want to just learn better models. Well, part of the tricky thing here is robotics data can be hard to collect. Like, you generally have to run a robot. Well, some people have gotten around that by doing massive simulations. So this is becoming a common approach. This is, again, Marco Hooter's group. And they're training this quadrupedal robot to walk by just simulating it tons and tons of times. So that's one approach. The other one is to just buy a bunch of robots. So that's what's happening on the bottom. So then you can collect a bunch of data that way. But this isn't necessarily possible for all systems. Like the Mars rover or our human interactive robots, we don't necessarily have good ways of simulating them, and it might be dangerous or expensive to collect this data. And so what I've often done in my approaches to learning for robots is residual learning. So instead of just trying to learn the whole model of the system, we have all of this nicely constructed, well-studied understandings of dynamics from control, robotics, nonlinear dynamics, things like that. Let's use that and then just learn the residual. So we can use our theoretical model to help us extrapolate and interpolate, and then just fine tune with our learned residual. The other thing we're going to do is we're going to learn episodically. So we saw this was really useful in our preference-based learning. So we're going to continue that. This allows us to focus on the region where we're applying our robot and collect data around there. So the example case here is this planar biped robot, and we're going to try to get it to walk across these yellow stepping stones. So this robot can fall forwards, backward, and down, but it can't yaw and it can't fall sideways. And we're going to roll it out once, collect the data, retrain, and then roll it out again, and keep doing that until we get safe behavior. If we tried to robustify for this problem, it just wouldn't take a step forward, right? It needs to be able to walk across the stones in a way that counteracts for the uncertainty, not just stays robust to it. We're going to enforce safety for these stones by having one barrier function that pushes the foot forward and one that pushes it back. And so you see that here. We've got the blue one pushing it forward, the red one pushing it back. And since these are dropping below 0, we're getting safety violations, and our system leaves our yellow stepping stones on the bottom. So we then collected that data, trained again. We're going to run our system one more time. Now we're trying to account for the uncertainty directly in our controller. And we did better, but we also deviated and left our stepping stones. We do this one more time, and now we've identified this uncertainty and are really going to have to kick our system to really get its feet onto those stepping stones, and we're able to successfully circumnavigate this treadmill here. So just one more time. Oh, sorry. So the first trial here, we are just using our nominal model. There's a lot of uncertainty associated with this nominal model coming from motor viscosities, friction, contact forces, things like that we can't model perfectly. So we collect that data, train to try to understand the uncertainty, now apply our controller that counteracts for that uncertainty by directly canceling it. And we do better, but we still don't make it all the way around. Collect that data, apply it one more time, and are able to successfully complete this task. But in order to do that, we really have to kick it. So it gets this weird walking because it's not the nicest gait that it has to follow, but it has to really kick its feet to get across. Okay, so that worked nicely there, and I wanted to apply it to another interesting problem. Here we have a drone with a flexible cable tied to it and a water bottle attached to the bottom. That drone is here, if you're interested. So in this case, I'm going to say that safety is don't let the bottle hit the ground. So I'm going to assume I know the length of the cable and the payload, but I don't know the bottle state or the mass of the bottle. And I'm going to try to learn the effect of the disturbance. I'm going to try to learn the disturbance given the drone state. So I have a motion capture system and an IMU that it can identify the state of the drone, but I have no idea what the water bottle is doing. And I'm going to fly the drone up to a position and then let it fall towards the center. This is going to induce some motion in the water bottle, and then the control barrier function is going to try to catch it. And so it looks like this. So I fly up. I've trained on some pre-collected learning data that I just flew around by hand. And I'm able to counteract that nominal fall. But if I move to the side, I have a small safety violation there. Like I don't quite achieve the safety that I wanted. I mean, as I move elsewhere, the same behavior happens. And I do okay, but I scuff the floor, which is violating safety as I defined it for the system. And okay, what happened here? I would argue that this happened because this learning problem isn't well posed. There's not a one-to-one mapping in between the drone state and the disturbance generated by the water bottle. And beyond that, the system's chaotic. So even if we could measure everything, it would be really hard to predict. And there's no one-to-one mapping. So like we really need a lot more information in order to predict what this disturbance is. And so this motivated me to switch paradigms. So we've been using this deterministic paradigm where I should be able to predict everything. But really, I can't predict everything here. There's a distribution of what the effect of the water bottle could be given the state of the drone. And so this is going to shift us to a stochastic perspective. What's the distribution of this disturbance that I could be experiencing? So that brings me to this third section here. And OK, if we're shifting paradigms, we now have to develop totally different guarantees. So that's what we're going to start off with. So this paradigm shift, we're going to move from continuous time, this x dot f of x plus g of xu, to a discrete time version of our system. And this is in part, there's a nuance to how stochastic differential equations and sample data systems play with each other. They don't work very well together. And so we're switching to this to better represent the stochasticity for robotics. But happy to talk about that more. But we're switching to this discrete time model for our robotic system because it better captures uncertainty. And then we're going to switch from this decay time derivative constraint to a decay constraint in discrete time. And I'm going to propose that we use this expectation-based decay constraint. There's a bunch of different ones you could use. You could use a quantile-based constraint, a CVAR constraint, things like that. I'm going to use this one, and I'll get into exactly why in the next slide. And then we're going to change our safety goal. Instead of enforcing 100% guarantees of forward invariance of our safe set, we're going to switch to trying to achieve bounded risk of failure over a finite horizon. And OK, the reason that I want to use this expectation-based constraint is, one, because it's kind of natural. Like, if you aren't considering the stochasticity, you just remove the expectation. That's your discrete time constraint. But if you are considering the stochasticity and you use this expectation, there is now a one-to-one mapping between this discrete time control barrier function and a super martingale. A super martingale is this expectation-governed process that is really well studied in stochastic process theory. So there's a lot of there's a huge wealth of information and theorems and things like that associated with super martingales. And we can transform our barrier function rollouts here with this safety criterion into rollouts of the super martingale through this identity. And now we have a different description of safety that just says we need to be below this line. And there's a lot of really nice martingale theorems that characterize whether or not we'll be below that line with some probability. So in particular, I use these two in my research, Ville's inequality and Friedman's inequality, which are just two different ways under different sets of assumptions to bound the probability of how concentrated our martingale is. And so I converted these lemmas. I was able to take them and move them from a super martingale context to a safety context, where now under different assumptions, we can get probability bounds of the safety failure over a finite horizon for these systems. OK, there's a lot of math here, but the main takeaway is we have this relationship between discrete time control barrier functions applied in expectation and super martingales. Yeah. Yeah.
What is the randomness?
The randomness is on the dynamics update. So this is our this is our system, and then the randomness is in the term D. And it's dependent on the filtration up to that point. Conditioned on the filtration. Yeah, yeah. OK. So there was a lot of math on that last slide here, these bounds with these different assumptions. But the key takeaway is that we get this bounded risk of failure under certain assumptions. And it's governed by these four different parameters. One is the initial condition of the system. One is the horizon length over which we intend to operate. Another is the distribution information. So this is like the variance of your distribution. And the last one is the safety decay rate that we're enforcing on the system. And so as the engineer, this is the one that is the most important to us. So this is the one we have the ability to tune. And as this goes to 0, we lose our guarantee. And as this goes to 1, we get stronger and stronger risk bounds for safety. So great, we've got some nice theory. How do we practically enforce this on our system? So we start with this nice theoretical constraint that's easier to understand. We've got this expectation of safety with our dynamics in it. But how do we actually apply this in practice? Well, it's a little tricky because this expectation is on the outside of everything, and our uncertainty is coming through our disturbance D. And so we're going to try to move our expectation onto that. Here we're going to leverage Jensen's inequality. So this is the case where I have a bounded Hessian for our safety function h, and it's concave. There's different things that happen when you have different types of concavity or convexity, but in the concave case, it looks like this. And we get a expectation now on the disturbance, and we also need the covariance of that disturbance as well. And I'm going to suggest that we learn these components through generative modeling. So we're going to try to learn the distribution of the uncertainty. And then the last thing here is we have this complicated dynamic. So this is a discrete time dynamics update that can be complicated with respect to our input and hard to optimize through. And a cool result that Andrew Taylor, Victor Dorobantu, and I found is that if you use the appropriate Runge-Kutta approximation, this can be a linear approximation of your dynamics, and you can still get good guarantees of safety for the simplified model for the sample data system. Okay, so now we've moved from something that was nice looking and theoretical to something that looks a little more complicated, but is practically enforceable. Each one of these things I can evaluate, and if our function h is concave, this is now a convex constraint, which we can enforce on hardware. And so we did that. This is our online risk-informed optimization controller. It's a bit of a backronym. We wanted it to be Oriole because it's a drone that flies at Caltech, and so we wanted an orange bird. But we were tired and couldn't come up with the last two letters. So we wound up with Oreo. And this combines a conditional variational autoencoder for our generative model with our discrete time control barrier functions to enforce safety. And applying back to our same problem as before, we're flying the drone up, letting it drop. Now we've trained our generative model on data that we've collected in order to capture the distribution of this uncertainty. And we get nice safety behavior. We're no longer scuffing the ground, but we're falling towards it, remaining robust to the uncertainties that are generated by the swinging water bottle. I would say that we get these stochastic guarantees, but that does require additional assumptions on those approximations we made to get it to apply, and also that the generative model is perfectly accurate. But assuming those things, then we get those guarantees that we had before. And this worked really well on our hardware here. So we took it out, used it as a demo, took it into a new environment, retrained it, switched the water bottle out. There's Dr. Ames in the corner. So this was a talk we did for folks who were visiting Caltech. So there's a whole audience where the camera is, where y'all are sitting. And I was like getting more confident with the system, so I'm really pushing it. We're getting some really cool flight behavior here. Oh. Okay, so that worked really well for us, and we wanted to then apply it to a different robot. Like, this was a successful demonstration. Let's see if we can generalize to other systems. And so just to warn you, this is an even worse backronym than Oriole was. This is safety on humanoids via CBFs in expectation on learned dynamics. And yes, that's SHIELD. So it's a cool name. The backronym doesn't quite work, but it's a really cool application of this idea. And so for the drone, we just tried to learn the effect of the water bottle and the dynamics, and then we can compensate for that by changing the actuation. For this walking robot, we shifted that mentality a little bit. And now the system that we're considering is the coupled robot plus the reinforcement learned locomotion controller. And so the inputs that we're going to apply to the system are just reference commands. We're going to modulate those reference commands in order to try to get good safety behavior. And this is, again, taking from that hierarchical approach that we heard about from Noel yesterday, and this kind of idea of separating the safety requirement and the tracking metric. So we're going to regulate those reference commands instead of directly regulating the joint inputs. And then this required a shift. So we couldn't just condition on the single previous state. We now have to condition on the history of states and inputs to kind of capture the higher order uncertainties in the system. And what we found that was cool, that extended beyond Oreo, is we could use this learned model of the dynamics residual to also improve tracking. So we're going to improve both tracking and safety using this setup. And we put this on our system. So the robot's either going to try to walk forward or stand still and avoid the people in the environment. You can see it's building its map of the environment on the bottom left, with all these red things being obstacles it's trying to avoid. And it's going to slide around Gary here, not collide with him. in this nicely unstructured, kind of messy machine shop. So the same thing's happening here, where we are learning the difference between the full order system with its RL locomotion controller and our reference commands. So that worked nicely. We now have two applications of this idea of, okay, let's apply these stochastic safety methods to practical systems. But these weren't particularly dynamic safety, right? I mean, the drone was moving quickly, but its safety constraint was don't hit the ground. And the ground's not really moving, like it's not super dynamic. And the humanoid also, same thing, it wasn't a super dynamic safety behavior. And so we wanted to push that dynamic component. And so in doing that, we had to overcome this problem that safety filters are inherently myopic. And so the approach that we've been taking previously is that we have a performant controller that's going to get us to our goal. Then we're going to modify it in order to achieve safety. That's our safety filter that you see up there. And this can cause some problems in its practical application. And that can look like this. So each of these black dots, if it just obeyed the regular controller, it would get to the goal star at the bottom. But we're then enforcing safety that says, don't enter our peanut. You need to not hit it. And because we're enforcing safety in a way that isn't aware of the performance and the performance isn't aware of the safety, we wind up with these stable equilibrium points that are marginally safe, like right on the boundary at the top of that top center of that peanut there. And this can cause really big problems for the practical application of safety. And we see that here in this demonstration. So we've got a quadrupedal robot that's trying to avoid getting hit by this dodgeball that we're going to roll towards it. And it also has to stay inside of this square. And you can see that definition back there on the back. And so what happens is the ball rolls towards it. It backs up towards the wall. It's like, oh, no, I'm going to hit the wall. I move towards the ball. And because it's not planning for performance, it gets stuck there. It has no understanding of what's going to happen over a time horizon. It's just myopically moving back and forth in between these two potential violations of safety. And we see that happening pretty repeatedly if we try to run these with dynamic environments. We get towards this marginal position in safety, we get bounced back and forth, and then we get squeezed into an unsafe position. And so planning can help with this. And this is probably really obvious to roboticists in the room. Like, yeah, you probably should be looking at horizon understanding in order to get performance. And so we're going to adopt a method from model predictive control where we can optimize for performance while enforcing a safety constraint. And this gives us much better behavior. So the top, again, we are trying to get to the goal, but we're going to wind up getting stuck at that point up top for a lot of the trajectories. But at the bottom, we have all of our initial conditions flowing around this peanut obstacle getting to our goal location. So now we're able to achieve safety. We're not hitting the peanut, but we're also able to achieve performance with everybody getting towards the star. Okay, now when I adopt a model predictive control framework for safety and performance, the immediate question that a lot of people have asked is, okay, why are you enforcing a discrete time control barrier function constraint instead of a safety constraint? The planner can enforce this just as well. Just make sure that your state stays above 0 along the plan and you'll be okay. And my argument for this is this row is super important. This decay constraint is what gave us our stochastic robustness before. It gives us a lot of really nice inherent robustness properties to this controller. So we're going to compare these two with rho equals 0 or rho strictly greater than 0. And so if rho is equal to 0, we don't have these additional robustness, and we end up getting hit by our ball here because we plan to move backwards, and we're going to try to move backwards. But with all the uncertainties in this system, we don't do it fast enough. We're not robust. We end up getting hit. And this happens across the board. This was really repeatable. There's not enough robustness for this system if we just apply a standard state constraint. Alternatively, if we have a value of rho greater than 0, we add robustness to the system and we get this really nice performant behavior. We move out of the way, avoid getting hit by the ball, and then return nicely to our goal position. And similarly, this worked for a bunch of different applications super repeatably. Okay. So we wanted to do that also on our quadrotor drone. We have this nice dodgeball setup. So instead of rolling it, I'm now going to throw it. We're going to try to avoid the ball that I'm throwing and avoid hitting the ground. On the left, you see two third perspective cameras. And on the right, you see the onboard camera. And this is the actual frame rate that it's using. So it's running at about 11 to 12 hertz. And it's segmenting using a distillation of Facebook's segment anything model. And all of this is running on board on a Jetson Orin. And it's using a RGBD camera to get an understanding of where it is in space, segment that, use that to get the measurements for a Kalman filter, estimate the state of the drone in the Kalman filter, and then run our model predictive CBF controller to enforce safety. What's really cool is if you enforce safety on the Kalman filter belief state, then naturally you enforce this expectation CBF constraint on the system. And okay, so if we run just with no planning for our quad rotor system, this is what happens. I'm only going to show this in simulation because it is not something we want to put on hardware. It just runs away forever. And this is what you might expect, right? It's just saying, I need to be safe, and right now the thing to do to make me be safe and not be hit by the ball is run away. Similarly, we don't want to apply our state constraint model predictive control because we try to get out of the way, but it's not robust enough and we end up getting hit. But our MPC with the CBF tightening really nicely has this avoidance maneuver. And we saw that again on hardware. So I like watching the right-hand side because that's really what it's getting. It's getting like 4 or 5 frames to estimate the ball and plan and move. And it's getting out of the way here. I'm also particularly proud of this because we started with those quadruped videos at like ×8 speed, and now we're down to 0.2. So I've really pushed from not dynamic safety, conservative safety, all the way to dynamic safety here, getting really quick motions in order to ensure safety for the system. We're tossing the ball at around 6 meters per second. I did a couple of tests where I had OptiTrack markers on it that aren't shown here, so we can get ground truth information. So I'm about a 6 meter per second dodgeball thrower.
What's the frequency of the system?
11 to 12 hertz. Yeah. So that was our big bottleneck, was running the segmentation fast enough. But because we're running this fancy segmenter, we can also toss other obstacles. So this is a Mario Kart green turtle shell that it's trying to avoid. And you can see the uncertainty in the vision map, like it snapped over to my hands at the end of the test there. But we're getting this nice dynamic safety where we're avoiding in a way that I had to slow the video down to interpret. Okay, so that was my work here on the center 3 components of dynamic safety under uncertainty. And so now we get to look at some fun stuff of the takeaways and future work. So the way I structured this is we have takeaways on one side, and that leads me to future work and things that I'd like to continue from there. So 1, I found in the course of my PhD that conservative guarantees are still useful. Like, even though our robot didn't move when we tried to enforce all this robustness, that's okay, because it pointed us towards the knobs that we can tune to get the robustness we need. On one side, we might be performant if we turn the knob to 11, but we might be unsafe. And on the other side, if we turn the knob to 0, we might be super safe but incapable. And so there's some balance there in the middle that we want to identify, and that can allow us to achieve safety in this kind of interpretable way because we've identified these parameters. Now, the challenge for the future is getting better calibrated safety guarantees, because the guarantees that I had, martingale ones, or the worst case uncertainties, these are not very well calibrated. Our bounds are loose, they're really conservative. And so future work here is starting with the system, passing it through some nice, well-calibrated guarantee to get the perfect tuning of our knob that we want. Additionally, another takeaway is that we can enforce safety requirements. Like, this is huge. We've been able to start with a safety requirement, build it out for the full system using this separation idea with this tracking metric shrinking. But this kind of assumes that we start with a safety requirement. And a lot of times, because we're starting this way, we enforce safety for collision avoidance. But really, safety is a more general idea than that. And where does this safety requirement come from? So like in this trolley problem, this isn't collision avoidance anymore. Safety for this system is pulling the lever and making it hit the tree and not the puppy. But how do I write that down mathematically? How do I generate that on the fly? Once I have it, I can do the stuff I had on the left. But how do I get this safety requirement description? Another thing here is I found across my PhD that we can use learning to improve confidence and move from these worst case conservative guarantees and performance over towards more performant behavior with risk awareness. But how do we evaluate the confidence as we move across the way? How do we know when we can use one and the other? How do we know how to blend these given a variable level of confidence here? And how do we evaluate that? I've also found pretty consistently that it's easier to learn residuals than it is to learn the full model. This allows us to leverage, a lot of background knowledge from control theory, dynamics, robotics. But how useful is this really? Are there edge cases where this doesn't work? What is the utility of our theoretical models? How do we bake them in the best way possible? And the last one that I think is really important, and I think one of the biggest lessons I learned during my PhD, is that safe control requires robust implementation. It's not enough to just build a safe controller. If your underlying system has a bug in it, doesn't matter. So we really need to be building safety kind of from the ground up. And this is where I get to show some fun robot bloopers to describe what I mean by that. So when I talk about the drone, I often think of it as 4 unhoused blenders attached to a chemical bomb. Because those rotors are pretty sharp, and the LiPo battery, if it breaks, it'll catch on fire, and you just have to wait. So this is not a safe system. The drone and I have a mutual respect for each other. And in this case, I'm running a safe controller, quote unquote, robustly safe controller, but I have a bug where my thrust calibration is wrong. And that's going to cause some problems. So there's volume for this. So I don't think it's too loud, but it's fun to hear. Sounds like R2-D2. So it tries to get out of the way of the ball. It's getting way more thrust than it asks for, and hits the roof, hits e-stops, falls to the ground. Similarly here, we're running our system, forgot to remove the simulated obstacle. And so it's like, oh, there's an obstacle in front of me that's only in code. Hits the roof, gets caught, hits the e-stops, falls to the ground. This one was the craziest one. This one took me like a day or 2 to figure out. So it's been working fine for like 10 minutes of flight, and then a bad message of data resulted in a message that was all zeros, which passes a checksum because the sum of 0 is 0, and that reset the reference quaternion. The reference quaternion got normalized from 0 to garbage, and then it's trying to track garbage, and out of nowhere, it just whoop. Oh, and then watch my face on the top right. So I wanted to catch it, and that split second, I really, really wanted to catch it, and then I remembered it was a blender. So I really think that as we build safety for these systems, it's been great to work on these safe controllers, and it's really nice, especially in this lab, to be able to work on that component of the system. But as we build safe systems, we really need to think about it from the ground up. I should not be building both that and the low-level controller, because clearly I built some bugs into it. But we really need to be thinking about how safety manifests in the whole stack. And so just kind of the thesis statement, I suppose, of this is robust safety guarantees provide a structured framework that can be enhanced by data-driven and planning-based methods to achieve dynamic safety under uncertainty. And my contributions to this thesis are robust safety methods with worst-case assumptions, learning and planning-based methods to improve performance, and risk-based safety with practical enforcement methods. So now, here's the bibliography of the things that I published during my PhD. I was able to at least cite the first 14, but 15 through 21, happy to talk about offline other things I worked on as well. So I've heard from other people that research can be lonely. That's never been my experience. I had the great privilege of working with some really amazing colleagues. I think this is everybody that I've ever published a paper with. And it's just been a huge privilege to work with some really amazing people. So thanks to y'all. Thanks to my committee. So Dr. Ames, thanks for taking me in as an undergrad from Berkeley, was interested in robotics and control. It's really been an amazing time. The opportunity to, put intellectual pursuits first and foremost, and the freedom to do that, and then put it on hardware also. It's just your support and direction in that, I can't thank you enough. So. Joel, thanks for all of your advice over the years. I really appreciate your door being opened and answering questions on life and research and job applications and things like that. I really appreciate your perspective. Yisong, thanks for all of the support. I really felt like I had somebody in Annenberg watching over me across the years. So thank you so much for all of your support and help. Gunter, thanks for everything. Choosing to TA for your class and the opportunity to TA for your class changed my trajectory entirely. I appreciate that opportunity so much. I really admire the impact you have on your students, and I hope to have, and the impact you had on me. And I hope to have that same one when I move on after this. Preston, I know you're online somewhere. Thanks for being in the basement doing martingales with me and just being the best mentor and friend. And I'm so glad I could have you on my committee. Thanks to the other mentors and teachers that I've had across the years, Katie and Joel Trop at Caltech, who really were influential in some of my earlier research and then the martingale stuff. The folks at NVIDIA, Marco Pavoni, Yuxiao Chen, Karen Lung, who radically changed my understanding of safety in about the 3rd year of my PhD, shifting it towards, okay, what does this mean for real world systems? How do we develop and deploy these things? The folks at Berkeley who were pivotal in getting me started in engineering and research, George Anwar, who came all the way down from Berkeley to be here. Thanks so much. You're really influential. to my trajectory across through academia. And then to my Science Olympiad coach, Jessica Bloodstone, my 5th grade science teacher, Chris Mika, who just like started me on all of this. To the MCE staff, so Jenny, Michaela, Lynn, Kristen, Leslie, y'all are the ones who make this department run. Especially Michaela, you're like the WD-40 to our squeaky engine. Like we would not run without you. So thank you so much for everything you do. To the folks in the Amber Lab, especially Andrew Taylor. So Andrew Taylor was a 2nd-year grad student when I started, or 3rd-year grad student when I started, and essentially was my on-the-ground mentor for 4 years, like really took me under his wing, showed me the ropes. Like, Andrew, thank you so much for everything. Like, I couldn't have done this without you. And to everybody else in the Amber Lab, congrats to Dr. Knoll. And go Roomba Broombas, our softball team. It's been really amazing to be a member of the lab, being surrounded by all these really brilliant people. Just keep pushing. You got this. To the grad school friends, thanks for everything. You've really made Caltech home over the past 6 years, and it's been such a huge pleasure. So most of you probably know this. I was the head of the triathlon team for about 4 or 5 years of grad school. We had 3 practices a week, 4 races a year. And it was just the best group of people. Like the folks who started with me, Angus, Stephanie, Miles, Newton, William, like Annette, is just like the most wonderful group of people that really carried me through grad school. And I'm really honored to the folks who are continuing on the club after me. Nikhil, Han, Ethan, thanks so much for all the work that y'all are doing. So most of you probably know this, but I used to live up in Altadena. These are pictures of my garage and my car. And I just really feel like I need to thank the Caltech community for coming together and helping me through this really tough time, especially my like adoptive roommates, Ethan and Quinn, who really took me in when I needed emergency housing. So just this outpouring of support from the community was really amazing. So thanks to the Caltech community for that. I couldn't have asked for more. To my Berkeley friends, especially Chris, Joyce, and Carson, who could be here in person today, thanks so much for like reminding me what the real world is, reminding me how special grad school is, and like I can focus on intellectual pursuits in a way that like people in the normal world can't. So thanks to all of you. Go Bears, Will Bones. To my extended family. So a lot of my family is in Southern California, so it's been amazing to be around here and be able to be close to them. Also to my family in Boston, Jack and Jill, who are online. Thank you all so much for all of your support. I'm excited to be in Boston with you pretty soon. And to my aunt, Dr. Jill McCaffrey, you are like the only person in the family who really understood what I've been going through. And so just thank you for all the support. It means the world. Can't wait to be in Boston. To the Blasio Munoz family, so this is my girlfriend's family, who just really have taken me in as one of their own, and I can't thank you enough for everything that you've done for me, so thank you. You've really made me feel like a part of your family. To my nuclear family, Mom, Dad, and Ian, and Sky, our dog. Thanks for all of the support through grad school. Thanks for dropping by, pulling me out of lab to grab lunch and take a break, lift my head up from research. Like, it's been really special to be able to be nearby for the last 6 years. And to my girlfriend, Bernadette, thanks for everything. You mean the world to me. I'm really excited to move to Boston and be there with you. So thanks for all of that. And with that, happy to take some questions, and thanks all for being here. Yep, Nikhil?
I know at the beginning you mentioned that the safety guarantee failure for the measurement robust CBF is dependent on a bunch of Lipschitz constants, presumably at least the Lipschitz constants of the perception map itself.
Yep.
Function.
Yep.
I don't know if this is also that's also the case for this in the stochastic sense, but in the case where that perception map is not something that's super easy to write down, how do you get those? And
yeah, that's totally fair. Yeah, so when I started my PhD, I was trying to use like control theoretic methods applied to computer vision problems. And that's tricky because of exactly the problem you're pointing out. You have these massive Lipschitz constants that are really hard to deal with. That motivated us to move towards the stochastic lens where we can treat measurements kind of as this like uncertainty associated with them instead of trying to differentiate or find the Lipschitz constant of our vision map. And so that particular problem is kind of what motivated the preference-based learning stuff. So we said, these Lipschitz constants are huge, and we don't know what they are. And if we actually applied it to the system, we probably couldn't do anything. So instead, we tried to define the actual values. Yeah. And in practice, we found that pretty much across the board. And this is my point of like, robust safety guarantees are useful, even when they're really conservative, because they point us towards these tunable parameters. Like your Lipschitz constant pops out and you're like, okay, if that's the Lipschitz constant, I have guarantees. If it's not the Lipschitz constant, I probably still get good behavior, or I add some robustness, right? Yeah?
You have a layman's definition of stochastic, is that?
Probabilistic, yeah. So there's like, it's not super well defined. People kind of use them interchangeably. A lot of people use stochastic, probabilistic stuff. But my sense is that stochastic things are probabilistic things, but applied across time. Like they have a process to them. Yeah, and that's not a rigid definition, but yeah. In practice, a lot of people use that parlance. Yeah. George, yeah?
Yeah, so in this aspect of the, your robustness and based on safety, which is the criteria that you're doing it, in all of that design aspect, how do you determine the degree of the trade-off between aggressiveness
Yeah.
and the aspect of safety? Is it all just all together, or there is a tuning parameter?
There's totally a tuning.
Because notice on some of them, the movement were quite aggressive. But
Yeah.
do you actually tune that in, or?
Yeah, so in the probabilistic stuff, it's exactly that row parameter. So it's this decay rate. And you can tune that, and you're tuning the, like, by tuning it higher, you're accepting less risk, but you're getting less dynamic behavior. You're like letting yourself decay in safety less and less each step. If you tune it lower, if you set it to 0, you can go all the way to the boundary of your safe set in a single step, which like could work, but you're accepting more risk as you do that. And similarly with the worst case guarantees, if you tune your knobs down, you still get a guarantee. It's just not with respect to the worst case bound you set for yourself. It's with respect to something smaller. And so you can get more dynamic behavior, but your guarantee is for something less than what you expected.
So in some sense with that, you can also then design it in the sense that you allow your system to take more risk.
Yeah, absolutely.
in the balance.
Absolutely, absolutely. Yeah, so if you push rho closer and closer to 0, you allow for more risk. Yeah, Bree?
Like any kind of like where an area you want to see robotics apply?
Oh, that's a great question. I mentioned earlier that Baymax is my favorite robot. I don't know, have folks seen Big Hero 6? Yeah, some folks. By far my favorite. So Baymax is a nursing robot that's supposed to help people who need healthcare, and I think that would be a really phenomenal application. But to solve that problem, we need to make sure that robots are safe. This is similar to like robot childcare. Like we need our robots to be safe enough to deal with people and interact with them. So I'm hoping in my career to push us towards that capability.
We've got 10 seconds left.
You should tell everyone where you're going.
Oh, yes, I forgot. You didn't mention it at the start.
I forgot to mention it too.
So after this, I'm going to start as a assistant professor at Tufts University in Boston. So I'm moving to Boston. Bernadette's already living there. And I'm really excited. I'll be starting up a lab there, focusing on these kind of ideas.
If we let it know.
Yeah.